Okay, thank you, Thibaut. Good afternoon, everyone. So this is the second lecture. Today's lecture, this is the title I gave to Thibaut, and I tried to stay within that, multi-scale modeling of oral processing of chocolate. So I talked about general things on Saturday morning. Today I'm going to focus on one material, most of it, and mostly on oral processing. So this is the outline of the talk. I'm going to give you the aims of all of this work that we did, and then all of this is mechanical characterization, and how we did, if we used these on chocolate to get multi-scale models for two things. Chocolate is very important, of course, the texture and how it breaks on the first bite, or rheology and so on, which is basically this bit here, multi-scale mechanics models. But I'm also going to show you multi-scale heat transfer models. So basically with chocolate melting, of course, is very, very important to the texture as well as the processing. And this last bit in the end is what was advertised to be in my first lecture, and I took it out and I put it here. Hopefully we'll have time in the end to go through our work on digestion process. Okay, so what's the aim of this work? If we look at this diagram here for oral process, we got length scale here and time. So when you put a piece of solid food like chocolate is solid at the room temperature in your mouth, then it will break under the action of the teeth into smaller and smaller pieces. It will mix with saliva to form a bolus, and then it will get sheared between the top of your mouth and the tongue, and when it's safe enough, you will swallow it. So what's happening here in terms of engineering? So here, first bite will be solid mechanics. Then once it starts mixing with the warm saliva in your mouth, it will start melting. Rheology will be important. As it shears the surfaces, you get tribology. So all of these things, if you want to study the oral process of any food, you're going to have to look at all of these different disciplines. And this is what we did with these two fantastic PhD students that we had. So I'm going to give you some results from here. So the hypothesis is here that we have chocolate which varies in volume fractions of air being pumped into it. This is micro-aerated, so the average size is around 20 to 40 microns, which you do not see by eye, so you're not going to realize that you're eating aerated chocolate, to small volume fractions, about 10-15%. And we wanted to see what effect that will have on all of these processes. So we're changing the microstructure of the chocolate by having gas in the chocolate. And the hypothesis is that we should be able to see that in our engineering analysis here, so solid mechanics, geology, tribology, and so on. And that will lead to a difference in consumer perception. And for these projects, this was the key, to try and understand consumer perception. So I'm going to start with that. I'll show you some really complex diagrams. It took me a long time to understand this, and I'm not sure I quite understand it yet. These are called temporal dominant sensation tests that were done in industry. So basically, they give people the pieces of food that you want to evaluate. And you might not be able to see here, but all of these attributes at the end, I'll read them because you might not be able to see. Soft, hard, moisture, sticky, smooth, cooling, mouth coating. There's some other things here, powdery, crumbly. All of those attributes are there in front of the people who are consuming this product. And at any time, they can press one of those buttons to say that that's the dominant perception that perceived at this particular time, okay? And then it gets recorded. And this axis here is dominance rate, is how many of the people chose that particular sensation at that time. If they choose another sensation, then the previous one stops. And this is how these things finish and start and so on. And so this is how these are plotted. This is time, and this is the beginning of the oral process. Here, we know this is the end of the oral process because this attribute, the mouth coating, is a sensorial attribute. They do it after they swallow. So we're interested between here and there. And you can see there's two graphs here. There's one for 0% non-aerated chocolate and one 10%. And you can see there's differences here, right? Both in the length of these bars, which bars are chosen, which colors are chosen, but also on the dominance rate. Okay, so this peak is higher than that peak, for example. This line here, which is a red dotted line, it shows the significance line. So anything below that was not statistically significant, and anything above that was deemed to be statistically significant. So it's good to study those. So the aim is to try and understand that using engineering. Okay, so what is chocolate? We've got the 0% here and the 10%. First of all, I'll talk about the aeration. I hope you can see these bubbles here. There's 10% by volume here, and there's no such bubbles in here. I don't know if you can see them, but there's also particles here. And the pores and the particles are around the same length scale. But we are going to treat the chocolate as a continuum, okay? So the only difference is that this one has pores in it and that one doesn't. So I'm not modeling here. I'm not going to try and model the different phases like I showed you on Saturday. This is the the pore size distribution. And you can see the average is around 2040. So as I said before, you cannot see that with the naked eye. From SEM and XRT, we also did X-ray tomography. You can see the blue bubbles. And these are the bubbles colored by different color depending on the size. And if you look at SEMs, then you can see hard particles like this one here. This is a sugar particle. This orange label is the matrix. I think there's one here as well. There's not very clear here, but that's the matrix. So that's the soft fat matrix. And then we also have the pores in one of the two chocolates. There's no pores on there. And they're around the same scale as everything else. So the pores are the same scale as all the other constituents. So we wanted to do tests as a function of temperature because you put the chocolate in your mouth when it's at room temperature, or some people like eating it from fridge, but we didn't look at that, and rate. Okay, so we did tests like this. This is a cylinder of chocolate, and you squish it. And we also did them within an environmental chamber, as is shown here, such that you can raise the temperature and do the same tests under different temperatures. These are the videos. This is the 10% and the far one is the 0%. You can see there's differences here. These are started to crack a lot earlier. And here we stopped to flatten because the load has dropped to 0, which means there's a macro crack somewhere where it has gone across the whole sample. Whereas here, this is still going. You might hear the sound as well of the machine pushing down. And only there you can see that the force is dropping. So you can see there's clear differences. You only put 10% air in, and the sample seems to be fracturing a lot earlier than when it's 0%. And these are all the results from the test. So there's the basic slide here. We've got 9 graphs. Going along this way, you're increasing porosity, and going downwards, you're increasing temperature. Okay, so we have 0% porosity here, 10% porosity, 15%. And then we have 20 degrees, 25, and 30. Okay? And what can we see here? Well, if we go across for the along that way, we look at the 20 degrees, you can see what happens to the stress-strain curves. There's where the red points are shown, it means you get a crack. So even though we actually get data after that, they're not valid. Because as we said on Saturday, for your test to be valid, you need to have uniform deformation throughout. So you can see that they break at much lower strains. The stresses are dropping. The different rates here, the different curves are with rate. So this is a high rate, intermediate, and low rate. So there is a rate effect here as well. Also, the big difference, and you can see that effect of porosity everywhere. Okay, so as you increase porosity, the stresses, the fracture strains decrease, fracture strains decrease. And here, with the effect of temperature, you can see it has a very big effect. So the temperature will start melting around 20 degrees. So you can see from here to here, there's a massive change. This scale is from 0 to 0.35, as opposed to those two. That goes from 0 to 3.5. And these strains go from 0 to 0.6, as opposed to these to 0, 0.3. So the temperature reduces the stresses, and the fracture stresses and fracture strains. The other thing you know, what other thing do you observe from those two that's common, and then you don't get it on this row? What's the difference between this row and the other two? So here you can see that they all go up at the same slope. And then we have, as we said on Saturday, some rate-dependent plasticity, whereas here your curves are different right from the beginning. Okay, so there's completely different behavior once the chocolate has melted. And we think that how we explain that, that's the next slide, yeah. So we have, this is the chocolate with the milk powder, cocoa particles. This is a milk chocolate, by the way. That's why we have milk powder, sugar particles in a cocoa butter matrix. So a chocolate is made out of crystalline materials, cocoa, sugar, milk, cocoa solids. And the cocoa butter, which is from literature, is amorphous by an amount, 25% to 75% of it is amorphous. So we think the crystalline bit is the bit that basically the crystals are maybe sliding past each other, and it gives the elastoviscoplastic response, which was the response at the lower temperatures. So here, straight line and then different plasticity depending on the strain rate. And the when you go to 30 degrees, you get this more dominant, and this is why you get these viscoelastic curves, which are different right from the beginning. So strictly speaking, you cannot really calculate a Young's modulus from here because it varies with rate, whereas you could on these two. Okay, so that's those results. This shows exactly the same thing. These are the three cylinders at the end of each test at different temperatures. They've gone to different strains. As you can see, this is broken at 0.15, 0.2, and 0.6. This is what they look like. And if you put the stress strain curves together for 0%, just to see the effect of the temperature more clearly than the previous graphs, then you can see the big, huge change. Okay? Yeah, and this shows the modulus, how it changes with temperature. If it's normalized from the 20 degrees, it's a very similar effect on all of them. Okay, and then, so once it's melted, you can do a rheological test. So we put a bit of chocolate in parallel plate, which were, I cannot remember if they serrated or we had sandpaper. And they were heated to 37 degrees. And then this is viscosity versus shear rate for the different porosities. And you can see that the 0% is lower. As you increase the porosity, the viscosities are higher. And then they basically coalesce as you go to higher and higher shear rates. These are material models that are fitted in usually for chocolate, so we fitted them and it just shows like a good fit. And if you look at the literature, these are storage moduli and loss moduli. Apologies, this is a linear range, and it only goes up to 50 hertz, so there's not a lot of data here. But all I want to show here is that the non-aerated chocolates give you lower moduli than the aerated. So when you put air in this chocolate, it seems to become more viscous, and it gives you higher moduli. So to me, coming from a solid background, that's not what you expect for a solid. If you put air in a solid, you're going to make it weaker, right? So this was interesting. But then, of course, people like a lot of you here know about this already, the capillary number. So if you have capillary number is the shear stress. So this is the viscosity of the solid, the chocolate basically, times gamma dot will give you the viscous stress. And then if you divide it by gamma, which is the surface tension over rho, if this comes down, rho is the, R is the radius of your bubbles, then you get a capillary number. And there's a lot of literature that says if you have a small capillary number, basically these gaps are actually acting like particles because the fluid has to go all around it. Okay, so it disrupts the flow. Whereas at high capillary numbers, then they are deforming, and therefore you get a drop in viscosity. So here, in these two cases, what is common is the chocolate is the same. So these two are the same, the viscosity and the surface tension. And the radius, the mean radius of the bubbles is the same. So this is 0, well, it doesn't have any pores here, 10%, 15%. They're the same average radius. So the only thing that changes is gamma dot. And you can see that as it increases, all of these three are coming together. Yes? Okay, so you have a difference in the here, you mean, yeah? Okay, so the hypothesis is that if you put these bubbles in your chocolate, you disrupt the flow, yeah? So the more and more of those you put in, the higher the viscosity will be, yeah? But as you're increasing your rates, then these things are actually deforming, and it's as if they're not there anymore. So they're not. So you can imagine that those are becoming very flattened, and then your flow is just as it was without the pores. Does that make sense? More questions? Sorry, I forgot to say you can ask questions, of course, as we go along. Okay, the next thing I want to show you is that we did fracture tests. We talked about fracture mechanics again on Saturday. This is a common test here that we do for solids. So you have a beam where I'm not sure you can just about see it. You make a notch, a pre-notch here in the center of length A. And then you support this at the two ends, and you have a probe at the top, and you push it down. Okay? And then you measure the load and deflection. As that crack here, there's a crack here, it will start growing. You can do this test at 20 and 25, it's fine. But we wanted to see what happens to chocolate as it heats up. You cannot do such a test for 30 degrees. The material is so soft. If you put it on the supports here, it will just sag under its own weight. There's corrections you can do for that, but really then you don't have much trust in your data. So what we're doing instead in that case is we're supporting the beam on a plate, so it doesn't sag under its own weight anymore. And then what you have up here, I don't know if you can see, this is a holder. There's a wire. There's a thin wire, and you push the wire down into the soft material. As you're pushing the wire down, you're creating two new surfaces, and you can say that this is a fracture mechanics type of experiment for softer materials. And you can see here, I'm doing this test at different diameters of the wire. This is 0.5, 0.25, and a thinner one, 0.125. The reason we're doing this, I'll explain in a minute. So first about the straightforward one, that's called the three-point bending, by the way. It's called the single edge notch bend. So that's the three-point bending one with a notch. There's standards for plastic, so we just took them. Of course, they're not for chocolate, but we took them. We tried to stay within those as much as possible. And again, we discussed plane strain conditions, the importance of that on Saturday to make sure you get the minimum value of the critical energy release rate. There's a notch that you have to put before you put your sample to test it. And then we did the test at 0.02, 0.2, and 2 millimeters per second. So this is how fast your probe is at the top. We went to compare these two types of tests at the different temperatures. Right, so we want to compare these and those. So we're going to get G from both of them, but what will the x-axis be, right? In this case, as the wire comes down, the crack follows the wire. So you can plot all of your results here as GC, which you're trying to get, as a crack speed, because it's the same as your displacement rate. You know what your crack speed is. In this case, you don't know what the crack speed is, right? All you're measuring is not the same as your delta dot here. And actually, you get non-uniform strain rate here. But there is an analysis you can do, and we did that to try and get the crack growth from these tests here, which are called the SENB. So we did that. I won't show any details. So this is what this says, needs an analysis to convert to crack speed for comparison with wire cutting data. For the wire cutting analysis, imagine here you have your piece that you're trying to characterize. You've got a wire here that's pushing down. As your wire pushes down, if you assume that there's plasticity around the wire, then you're going to push against a normal component on the wire as well as a tangential, which will be the friction. And if you assume that this has plastically deformed in front of here of the crack tip, then these normal stresses will be your sigma y, and the tangential forces will be mu f sigma y. Anyone knows what mu f is? When you have friction, you have the frictional force is coefficient of friction times the normal stress. So you can do an analysis here with equilibrium and so on. And you can see, of course, that what do you think will happen as you increase your diameter to plasticity in front of the wire and dissipation? Will it be as you increase your wire? Will you get more dissipation for plasticity and friction or less? More. Okay, so actually this is why we then do tests for different wire diameters, okay? Because then you can, basically down here, if you do the test at different rates here, at different wire diameters here, you get your cutting force here and the displacement. You're going to get curves like this. So this is the initial indentation, but then you get a steady state cutting, and that's the force that you want. And you do this as a function of increasing wire diameter. So the idea is that you can then extrapolate to 0 wire diameter, because if you have 0 wire diameter, the idea is that you don't have any plastic dissipation, no frictional dissipation, and all you're measuring is the energy to grow the crab. Of course, you cannot do tests with 0 wire diameter. This is why you do different wire diameters, and then you extrapolate to 0 wire diameter. So this is the need for the different wire diameters. But you do that, and it works okay. So I'll show you some results. So these are the results for the tests from the 3-point bending, which you could do on the solid-like specimens, 20 and 25 degrees centigrade. And these are the colors are the different porosities. And you can see that if you start putting porosity into your material, your energy release rate, your toughness, is decreasing. So it's becoming more and more brittle, and that's okay, because usually this is what happens in solids. If you put pores in a solid, you're going to get stress concentrations, and then your toughness will go down. And the same, so that's 20 degrees and 25. They're very similar. If you compare the two, at 25 they start to decrease, the GC. And these are the results from the wire cutting test. So this is the extrapolation method. Here it's not so clear. This is crack speed. The different colors are the different porosities. It's not so clear what the trends are. Perhaps maybe for the blue one, which is the highest porosity, there is an increase, but the error bars are very large here. But if there is an increase, that could tally with what we said about viscosity, that it also increases with porosity at 37, that was degrees. And this is how you put the data together. So now we have the same axis, which is crack speed. And we have here the two, the blue and the red, are the SENB tests. The 3 graphs are for different porosities. And then the triangles here from the wire cutting. So what you can see here, the most striking thing, is that when you go to, remember these were done at 20, 25 degrees, and then these are 30 degrees from the wire cutting. There's a huge change, okay? In toughness, it increases. So all of these things are happening inside your mouth. So far we said that the stress-strain curves are changing. So if I go back to here, so there's the viscosity that's changing. There's all of this stuff that's changing as you increase the temperatures. And there's the there's the toughness changing with temperature as well. And all of these are happening simultaneously during the oral process. So it's a very complex process to try and understand, but we'll make our best to see whether we can make a headway at least. So there's a summary of experimental measurements here. What does the temperature do? It increases the toughness. It decreases the modulus and the strength because of the basically almost the change in the phase in the material as it melts. The microaeration, it decreases the toughness, the modulus, and the maximum stress at 20 and 25. But when you go to 30 degrees centigrade, the toughness is increasing. The viscosity at 37, it was measured, which is the temperature in your mouth, is also increasing. So coming back to those tests I showed you at the beginning, can we use what we measured to explain those? Before I show you that, I also want to show you the results of one last test that we did. Yes, you got a question? Yeah. And I'm not changing the... Yeah. Well, that's the assumption that we make. Yeah. But you have to make some assumptions, otherwise you don't get anywhere. Yeah. Okay, so this is the test that we did try to do as close as possible in vivo, happens in your mouth. So you take a small sample like this, is about 12 millimeters. 0 and 12% aerated, right? And we put them inside a plastic bag, and we gave them to volunteers, students, fellow students, and we told them to put them at the back, the molar teeth, and do that, okay? And then because they're in a bag, you can also take it out and then measure the fragment size. And these are the fragment sizes from 0%, 12%. You cannot see it so clearly. These are the photographs that we digitized. But then what you can do is to measure the particle size distribution. And you're going to get a curve like this. This is the cumulative frequency. And this is the diameter. The black lower curve is the 0%, and the top curve is 12%. So you can see that for smaller diameters, you get a lot more smaller fragments in the aerated chocolate, which kind of agrees with what we said, that the GC is decreasing because of porosity, and that creates more brittle material, and it fragments into smaller pieces. Okay, so we got all this information. Let's see if we can try and explain this complicated thing. All right, so the first thing that we're going to discuss is this bit here, this here, the softness, which is here, and hard. So what you can see is at the 0%, there's hard. There's nothing here on hard. Nobody said that this 10% chocolate is hard. This is 0%. And then the soft here is narrower and lower dominance than this one. Okay, so I think that's okay because it kind of agrees with what we measured. We had a reduction in modulus and maximum stress with microaeration, and reduction with temperature, which led to an increase in the dominance and the duration of the soft perception by such an amount that hard was not picked up at all, the aerated chocolate. Then the next one I'm going to look at here is this bit here, the cooling. This says cooling. So here what happens after the soft hard, if you start seeing things like cooling, basically as the chocolate melts, it needs energy, so it provides a cooling sensation in your mouth. And this was picked by 0% chocolate, but not here at all. So the 10%. So we said here that the hypothesis is that because the GC, the toughness has decreased, we had increased fragmentation, so as we showed in your results, which meant that you get more smaller particles, which expedites the melting, as I showed you earlier. It speeds up the melting, and therefore you don't even sense it here, right? And this is what eliminated the cooling sensation in the micro-aerated chocolate. Right, so there's also a difference on stickiness. So for here, we did some experiments where we had a piece of chocolate here, and you have a tribometer, and you measure the coefficient of friction. And if you look at these results here, so this is level of aeration, 0%, 10, 12, and 15. And you can see that this is a coefficient of friction. It drops, whether you do it with artificial saliva or not. The coefficient of friction did drop. We never managed to understand why that was. But anyway, that's the results. And you can see it here. This purple thing here is stickiness, which appeared in 0%. And it did not appear at all at the 10%. So we said that the drop in friction by 25% meant that stickiness was not picked up in the micro-aerated chocolate. And then I think there's one more that we can discuss, we try and infer, is this smooth. There's a smooth perception here, which smooth is basically whether you feel particles in your mouth or not. And you can see that here, it's a lot narrower, and it's lower dominance than it is here. So this is wider, and it has a higher dominance rate. I mean, a lot of this is speculation, but we're going to have to try and explain something. So we said that the increased viscosity at 37 degrees possibly means that you're coating particles more and you're not feeling them. Again, I think this is speculation. But also the fact that we decreased GC during the first bite, it led to an enhanced fragmentation at 20, 25 degrees. Okay, when the first bite will be, these will be the relevant data at 20 and 25 degrees. And then you got smaller particle sizes, which sped up the melting, and then it could make this increase in the smooth perception here. Okay, the last thing I want to say about here is that we think that this is first bite because you got the hard and soft. Once you start getting cooling, then you know the heat transfer is important. Okay, and then things like moist and smooth, you know that it's a bolus, so we're measuring rheology and tribology. And then the mouth coating is when it ends. Here we didn't get cooling, so we don't really know when it started melting, but when you start seeing things like moist, we see the heat transfer must have started being important from that level onwards. Okay, so the test I showed you earlier, these are dynamic sensorial measurements that are happening as people are eating the product. So there's another type of test that you can do, which is static. At the end, basically you consume something, or you put it in your mouth, and then you do the sensorial examination. And the important thing here is to see the sweetness from the two materials, the 0 and the 10%, is about the same. And remember that for the same volume of chocolate, one has more air than the other. If it has more air, it will also have less sugar. So you're actually consuming a healthier product because it has less sugar, and you didn't realize it's not seen as less sweet, even though there's less sugar. So basically, there's a lot of sugar in the material we don't even sense. So by putting the pores into the material, it fragmented into smaller pieces. Maybe you have a bigger surface area that comes into contact with your taste buds in your mouth, and therefore you feel the sugar, even though it's less than the non-aerated. So this just shows how important it is to the structure, basically, in your material. It will change its behavior in engineering ways, but it will also change sensory attributes and potentially your health as well. The question is here now, so can we build a digital tool so that we can, these things that I showed you, can we model them? Can we have a model which will reproduce what we're measuring experimentally? And basically here the question is, I've changed the microstructure, I put gas, yeah? Can I predict what the change in the thermal properties will be in the macro scale? And can I predict what the stress strain properties will be on the macro scale? So we have two multiscale models, which will be for thermal and mechanical properties. So that's what I'm going to show you. So there's those two studies. So I'll start off with the heat transfer. So we had a beam of chocolate, and we built this rig. So this is your chocolate here. And basically all of this complex thing, what it enables you is to put different temperatures at the two ends of the bar. So I'll be showing you two types of tests where we put both ends at 45 degrees, and then the second test was at 45 and 16. So between 28 and 34 is the phase change of chocolate. This is the bar of chocolate. You can see the temperatures changing. This is from a finite element model. And it's basically put inside an insulated sleeve here, such that we can make this as close to as possible at what we're modeling. I'll show you some results from that rig. So we're measuring the temperatures at 3 points. Forgot to say that. Let's go back. So we're changing the temperatures at the two ends, and we're measuring the temperatures with thermocouples at T1, T2, and T3. T2 is right in the middle. T1 and T3 are away from the ends, and they're not symmetric. This is closer to that end than what that is. So we have, we've got these results here. T2 is the middle bit here. So it hasn't heated up yet when it's 45 degrees at both ends. The colors are different porosities. So chocolates, 0, 10, 15. And then on this side, we have the second test where we had cooling on the other side. So about 16 degrees here. And these are the sort of measurements that we get. And you can see by putting pores in, you have a lower steady state. So as you would imagine, by putting pores in, you're making more insulation in the material. And this is why foams are good at insulation. All right? So this is what you would expect. Okay, so from measurements like this, we were able to do finite element simulations, as is shown on the previous slide, where we have a macro scale bar. We're not modeling the pores here, and then we're modeling the two temperatures at the other end, and we try to match the model temperature distribution to what we measured here to inversely calculate what the conductivity is of the material. The conductivity of a material gives you the rate, how if it's a good conductor, it will conduct heat very quickly through the material. I do not want to restart my, go to snooze, please. Apologies for this. Hopefully this will work. Yeah. Okay. Okay, so that's how we got the conductivity. And then the next thing that you need, next two things for heat transfer, is the specific heat capacity, which gives you how much energy you need to put into a material with a unit mass to increase by a certain, unit degree of temperature. And you do this by using differential scanning calorimetry. So we did it on the three porosities, 0, 10, and 15, the different colors. And these are the measurements that we got. On this side is the 3 chocolates and the cocoa butter along. We made samples of just cocoa butter, which is the matrix, remember, of the chocolate. So what you can see here is that we have this peak, which is where the phase change changes. This is the onset of the melting and the end of the melting between 28 and 33, 34. You can get the specific heat capacity here. And the area under here gives you the latent heat, which is basically how much energy you need to put into material to melt it. So from a differential scanning calorimetry, we got delta H, as well as the specific heat. The thing to notice from here is how much bigger the cocoa butter is, the specific heat capacity, than those. So the cocoa butter is more of an insulator than the chocolate is. So now we have conductivity, we have specific heat capacity, we have latent heat. That's all we need to be able to do a thermal analysis. And we start from here. So we have the microscale FE model. So this is a representative volume element with the pores. And we simulate this. We predict what the conductivity, the coefficient of specific heat capacity will be the effective one, the continuum. We put it inside the macroscale tests, which are just the bars, and we compare them to the experiment. So basically, this is to check whether this microscopical model will give me good predictions for what the effective thermal properties are for the macroscale. Before I show you the results, this is the X-ray tomography. And you can see there's rings of white around the pores. We talked to people who are experts in XRT, and they told us definitely this is not an artifact, so it's something there. And the reason also we had a look, we started wondering what's going on is because, I don't know if any of you noticed this here. Do you see the specific heat capacity here for 15% is higher than the other two? So the blue curves are a little bit higher than the others. Should the specific heat capacity of a material change as you put air into it? No. So this is something strange, right? So because remember, specific heat capacity is how much energy you need to put in per unit mass. If you put air, the mass does not change. So this is why we thought this could be important. We had a look at literature, and they said that very often around pores, the cocoa butter concentrates. So we have a ring, very thin ring of cocoa butter. And remember, I showed you earlier, the specific heat capacity of cocoa butter was a lot higher than the green curve, than the chocolate. So if there is indeed such a ring here of concentrated cocoa butter, it could lead to an insulating material, right? So we did 2 types of models. 2-phase is just the pores in the chocolate matrix. And then the 3-phase is one where we put the ring of cocoa butter around the pores. So I'll show you both of those 2 results. To do this, because we had the cocoa butter ring, we had to get the cocoa butter properties as well. I showed you the specific heat capacity already, which was this green curve here. To get the conductivity, we did it inversely by modeling modeling just this test at different temperatures, assuming various values of K, thermal conductivity, and seeing which value of thermal conductivity led to the measurements that we had in the experiment. So this is the results. So this is the experiments and how we fitted the K such that the model and the experiment fits. So we can inversely calculate the thermal conductivity. And we saw that cocoa butter also has a lower thermal conductivity than chocolate, not just a higher specific heat, but a lower conductivity. So basically, by putting the pores in there, it's much more difficult to make heat flow through the chocolate and melt. We wanted to make sure that these inverse calculations were correct for the thermal conductivity. So another thing that we did was to put a piece of chocolate on the Peltier plate. And then as this rises, we get a thermal camera. We can measure the temperatures here. And then we can check whether our models using those inversely calculated conductivities matched the experiment, and they did for both the chocolate and the cocoa butter, so that was okay. Right, so I'll show you the results. So this is what we calculate for thermal conductivity from a microscale model, from 2-phase and 3-phase. And you can see as you put more air, as you would expect, the thermal conductivity drops, so it becomes more an insulator. And then this is the specific heat capacity with porosity. The 2-phase model doesn't give you any change with the porosity, but if you do the 3-phase, the ring of cocoa butter, which has a higher CP, then we get these lines here, and these are the experiments. So if you do that, then you do actually get the increase in specific heat capacity, which we measured. Of course, this could be important for processing, because when you do chocolate, it cools, and if you have these rings, they might change the cooling rate. The crystallization of the chocolate is very, very important, but also maybe the oral process, you know, how it melts in your mouth. Okay, and these are the results, final results from what we get from so basically now we know what the effective thermal properties are from the microscale, and we feed it to the macroscale, the beam, which is heated at 2 different temperatures at the 2 ends. And we get the black lines, 3-phase and 2-phase models, and the experiments at the dots for 10% and 15%. You can see that the models, these are not 0, this starts from 23, so this is a small difference. And the 3-phase models are closer to the real experimental behavior, but we were quite happy that we get close agreement. And this was for the heating 2 ends experiments, which is harder to predict because then you get melting as well. This is heating and cooling on one end, and here the agreement was better, but again, you see that the solid lines are closer to the experiments. And of course, the difference between these two is bigger here than here. Why is that? So remember, the difference between the 2-phase and 3 phases, we're putting that ring around each pore, right? So if you get more pores, then it will have a bigger effect. So that's why here is a bigger difference. Okay, so remember I showed you this earlier. I only discussed sweetness, but there's also a melting time. So the 0% had higher melting time than 10%. This is people, as they ate the chocolate, what they measured. So can we prove that more instead of just saying it's smaller? It breaks into smaller pieces, therefore they melt faster. Can we prove that? This is what we did here. So remember those pieces that people had in their mouth, and we collected them. You can take a picture of it if you let them on a table, and then you can pass that information into a finite element model exactly as it is. And then the boundary condition is that you put a high temperature, 37, the mouth temperature, all around the surface. Okay, and then you see how it melts, because I have all the thermal properties now. And we did that for both chocolates. One here is 0%, and this is 10%. So when I press the return button, you're going to see that this is temperature. They're going to start heating. The temperature goes in from the surface to the middle. And we did an little artifact thing that once it melts, it will disappear. Okay, so obviously it doesn't disappear, but we just did it for visualization. So you can see what happens from the 2 simulations. The small particles will melt first. But you can also plot the melted area in the two chocolates as a function of time. And you get this graph here. So this is 0% and this is 12%. So because the smaller, the toughness went down, it went to smaller pieces. Even though the thermal properties went the wrong way, that you would think that it would melt slower because you increase the thermal conductivity, you decrease the thermal conductivity with the inclusion of air and you increase the specific heat capacity. The fact that mechanics also changed and you broke into smaller pieces, it made up for that effect and more. And now you're melting the aerated chocolate much faster than the 0%. So that's why in that sensorial attribute, people saw that as well. Okay, so what we're saying here is that this fragmentation is very important in your process from the first bite. So I think, this is my view, of course I could be wrong, but I think it's wrong to study oral process just from rheology, because rheology is the bit that happens after you processed your mouth and it mixed with the saliva. You missed an important first step, which is the first bite, the fragmentation. That sets the chain of events that follows later on. So I really think that that first bite and the fragmentation is very important. Of course, people will say I'm biased because that's my that's what I'm working on, solid mechanics. But anyway, so this is very important. And we saw how it expedited the melting process, increased the fragmentation. It could increase the flavor intensity because of the sweetness. So the aim here is we model the thermal properties as a function of the microscale. Can we model that first bite and the fragmentation as a function of the porosity? And that's the second type of model that I'm going to show you. Before I show you that, just to get a recap, a little breather. Anyone knows where this picture was taken? I took that yesterday morning. Has anybody seen this in the village? It's in the Greek church, correct? As you walk in, it's immediately on your right. It's a really nice church. I was very surprised to hear that there's a Greek history here, so I just dropped in yesterday morning. As you go, it's a really beautiful church. It has lots of stuff on the walls and icons. As you go in on your right, where the stairs are, there's this wall painting, which I found really extraordinary if you look at this. So then there's also some dates here. So there's where is the first date here? There's a 1731. There was another date here, 1680 or something. Can anybody see it? I don't know where it's gone now. And then there's 1775. So this picture shows the Greek refugees coming on a boat. This is the priest and icons. Apparently they brought 4 icons with them. I couldn't see them in the church, and I'm assuming they're not going to put them there in display when there's no one to watch out over them. And they landed, the Genoese, which had the Corsica that time, they gave them permission to kind of inhabit a place close to Cargèse, not Cargèse. So they went there, and they lived for a few years. The Corsicans wanted to get rid of the Genoese after that, and they wanted to do an uprising, but the Greeks didn't want to do that because the Genoese are the people that let them stay here. So it created the friction between the two, the Corsicans and the Greeks. So the Greeks had to flee to Ajaccio. I checked this date, the 1731. Okay, do read it now. This is 1675. This is 1731. So I'm guessing this shows the Greeks leaving and going to Ajaccio. And then there's another thing here, 1775. I tried to find out what happened there. If anybody knows more than me, please correct us. But I think what happened then, French took over Corsica, and they took an interest in these Greek immigrants, and they allowed them to come back to what is Cargèse now. So I thought it's very interesting that these people basically painted their story on the walls of their church. If you do go there, I encourage you to go and have a look at it. It's striking. And then, I don't know if you've seen this yesterday on your boat. I'm not going to try and pronounce that. How do you pronounce that? Yeah. So this was taken yesterday. We went by car. I think you've seen these dramatic rocks already by boat. It was when you went with your boat ride. This is pink granite, and it is very dramatic scenery, and it's an UNESCO protected heritage site. I don't know if you saw this bit here. Did you manage to see this? It looks like a heart. Depending on if you stand at some particular place, you will see this looks like a heart. So a heart on a pink granite. I thought that was very, very nice. Okay. Right, well, now we're going to move on to our next multiscale model, which we said we're going to try and predict the mechanical properties from the microscale properties. So these graphs, what I'm showing you, are basically some of the graphs that I showed you earlier on. These are stress-strain curves. Here I'm showing you also tension compression. Before I showed you just the compression curves at the different rates. For 2 chocolates, 15% aeration, and then non-aerated here. And you can see the differences is what we saw earlier. This bit is the zooming in of the tensile curve. So you can see that in tension, the chocolate breaks at a much, much lower stresses than compression. And we did that for different type of chocolate just to see whether that indeed was the case, and we found the same thing. So these are the stress-strain curves in tension and compression. Here, compression is plotted as positive. And you can see that the maximum stresses are a lot higher in compression. And here is a table that summarizes the modulus difference in tension and compression. Also, the modulus was different, but not by much, 160, 120, and there's some error bars. But definitely the strength almost doubled, going from tension to compression for both of those rates. So that's what this says. And we think the reason this is happening, again, you have to look at what chocolate is made from. It's cocoa, sugar, milk, all of these are particles, the particulate phase in the cocoa butter. And we think that this particulate phase is what soil mechanicians already studied very well, that you get, because of the granular behavior, you get higher compressive than tensile strength, okay, because these little bits together, when you push them, they will be strong, but if you try and pull them apart, they'll all break apart. Whereas the higher tensile and compressive Young's modulus, even though it wasn't such a big effect as this one, we think it's down to the cocoa butter, and the chains may provide stiffer response in tension than in compression. So that's why we think you show these two behaviors. I have to say that in our models I'm going to show you now, we ignored this change in the Young's modulus, which is good on average, but this change in the strength, we took it into account. Okay, so the idea is that I want to model this, the fragmentation when the chocolate is in between your teeth. So this is the microscale model. So I'm going to try and model this, get the mechanical properties of this as a function of the porosity, and then fit these properties into here, such that I can then get a multiscale model for mechanics instead of multiscale model for thermal properties I showed you earlier. I've shown you this on Saturday. These are the stress-strain curves in compression only, and we fitted this phenomenological model for elastoviscoplastic materials. So you get an elastic response, and then plasticity, which is a function of rate. You can calibrate the constants in that equation with your data that you have for different strain rates. What we also wanted to do was to model the softening. You see, these are the curves that we get, stress-strain curves after the peak. And to do that, we use a damage model. Again, we discussed this on Saturday. So there's a damage variable D. I used capital D on Saturday, apologies. So here we're saying there's a critical equivalent plastic strain. If you're below that strain, there's no damage. And then as you're between this critical strain and some final strain where it will break, you get damage evolving according to this relationship here. I'll come back to that in a minute. And then finally, when you reach an equivalent plastic strain which is equal to your failure strain, then you reach a critical D, which then makes basically you get a crack growing. So in here, we've got an energy release rate, which we have measured. I've shown you how we measured this at 20 degrees already. And we also get a characteristic length L. So we need to calibrate L and this critical damage where we have complete cracking from our data. Okay, and this is what we did here. This is the experiments, the black lines and all the other things are the models. So we found that this characteristic length is about 80 microns, which is the order of the magnitude of the bits that you have, the pores and so on. And then the critical damage is 0.1. So basically, after this, the critical reaches 0.1, then you're going to get a crack inside your material. So that's how we calibrated our damage model. Okay, there's a problem with these damage models that they suffer from mesh dependency. So the idea for finite element analysis is that you can vary the, remember I talked to you about Saturday that you can have elements in you split your geometry into smaller elements. You should have small enough elements, because it's a numerical approach, such that you get the correct answer. So the first thing that you do when you do finite element analysis is to do smaller and smaller elements in your geometry and make sure that you get the right mesh-independent results. A lot of these damage models, unfortunately, they suffer from such mesh dependency. And this is a problem, because you shouldn't get different results depending on what your element size that you chose. And the default damage model in FEA software packages is basically going to do that. You can do your simulations at different mesh sizes, and you'll see you get different results. These are called the local models. So I'll explain in a minute what these are. What you need to do to make sure that you get consistent computations regardless of your mesh size is to use so-called non-local models. I'll explain in a minute what those are and how you do it. Okay, so on here, everything was a function of strain epsilon. Okay, so this is the symbol that I use, epsilon, which is the strain at each point, integration point is called on your finite element model. Instead of getting the strain at each point, which is the local point, if you average over a certain area and you get the strain here to be an average of its neighbors, then that's called a non-local model, and that's what you need to make sure that your results are mesh independent. And the way to do that, I mean, we use damage models in the literature. You need to solve this differential equation. This epsilon was the local strain, where I had all those damage equations. You introduce this E, okay, for non-local strain, and you need to solve this differential equation. Now, the fortunate thing is that this equation and that equation look very similar. This is the transient heat transfer equation, where if you put T, you can put the non-local strain. So there's actually subroutines in Abacus to solve this problem. All you have to do is to change the variables to think that these temperatures are actually your non-local strains. And it works quite well. Lots of people did that. And this LCH here is another characteristic length, which depends on the geometry, basically, of your length scale here. So if you're modeling something like this, it's in the order of, I can't remember now, actually, 5% maybe? I can't remember, of the biggest dimension. So that's what you need to do. And I'll show you the difference between the two models. So if you use the default local models, here what we have is we have a quarter of a plate, and I'm going to pull it upwards. Here, it's very small, you won't see it. I introduced the flow by putting properties here which are a little bit lower than the rest. So basically, when you're pulling this, you're going to get localization. Okay? And if you use the default local models for different mesh sizes, I hope you can see that here I have much larger elements than here and here. Then you can see this is the damage parameter, that here it localizes a lot more than here. And you get different results, basically, depending on your element size, and that's not right. Whereas if you use the local models, this again is the same problem for different mesh sizes, and you can see the three models now give you the same results. And that gives you confidence that what you're doing is correct. Okay, so we're going to start with the micromechanical model. So basically the model that has the pores in your representative volume element. And the first thing that we did was to increase the volume that we studied, just to make sure that we have a representative volume. Yeah? Yes. Okay, the L is this L, right? This P here. This is some percentage of the biggest length scale of your model. So it's not really a material parameter in this case. Yeah, so it depends on the dimensions of what it is that you're modeling. We got some, because there's a lot of literature on this, what it should be. So sorry, I forgot the number now. I can't remember whether it's 1% of your length scale or 10%. I really can't remember. But that's where we started from, basically from the literature numbers. And then we make sure it fitted the data. Yeah. I actually haven't used it for granular media, but I'm assuming, yeah, people have done it there as well. You're aware of people using that for granular? Yeah. Yeah, no, definitely here is not a material property. The other L that I showed you earlier, that is, but not this one. Yeah. Maybe we can discuss more at the coffee break. Okay, so we did various things for here we took the mean of the diameter, and we had models which had all the same size little gaps. And down here, we tried to reproduce the whole particle distribution with different sizes. So monodispersed means the same size, polydispersed means different sizes. And we also have, remember, the X-ray tomography, such that we could model it exactly as it is. We got this geometry, and we can fit it inside the finite element models. So we varied here the number of pores. Basically, the size of your RV will change if you want to keep your volume fraction the same. It will change as you change the number of your pores. So we wanted to see how big should the representative volume element be, how many pores we need to make sure we get consistent results. And these are the results I'm showing here. This is RVE size, and this is an average property. It could be the initial modulus, and you see they converge somewhere. These are different boundary conditions that you usually use for micromechanical models, the periodic boundary conditions and kinematic boundary conditions. But in any case, they both should converge somewhere where you say, okay, I need so many pores, that big, that size of RVE. And we found that we needed about 100 pores. So as long as this was big enough, sorry, the previous bit I showed you, basically I had 100 pores in here, then that's correct. It will give me the right answer. Then that's the first output that we did. We checked what the modulus was. So this is the modulus of the chocolate as a function of the non-aerated chocolate. And this is porosity. And we had 2 porous chocolates. We have all the results are on top of each other, but basically we have results where we digitize the XRT tomograph geometry. We have the results from the polydispersed and the monodispersed, and they're all about the same, as well as the experiment is the green one. These are theoretical lines. So for modulus, it's a little bit easier to get because there's analytical models that you can use, but it's the fracture that is more difficult and where you need numerical models. But this is how the whole of the strain curve is modeled, right? So here now, I am comparing the solid lines, and the dotted lines are experiment and model in compression and tension for the 2 porous materials. And we were happy that they were close enough. So we thought that basically our micro scale model gives us the correct properties, which I can then use on the macro scale, which is basically the piece inside under the action of your teeth. So this is what we did here. This is we 3D printed this from some scan data, and we just took this area here. And we made in vitro tests where we put this on an instrument machine, and then we have a piece of chocolate here, and we squish it between the 2 teeth. And then we did exactly the same on the macro scale, the finite element model. And of course, remember, we also did in vivo studies where we asked people to put the chocolate in their mouth and fragment it under the action of their teeth. So we got in vivo, in vitro, and in silico things that we can compare. This is a video of the in vitro test. And because we did it in a plastic bag, again, we could take the pieces and measure the size. And you could do the same, of course, in the finite element model. These are the experimental data that we got from this in vitro mastication tests for non-aerated 10% and 15% at different rates, 8, 10, and 15 millimeters per second. This is the rate that you squish down with the teeth. And you can see that the stresses are going down. So as you increase your porosity, which is what you would expect from the mechanical properties that we saw earlier. And this is how the numerical model predicts what would happen for the force displacement for the different porosities. So 0, 10, and 15 are the different colors. And you can see they're quite close in numbers, but also qualitatively. You can see the deformation here in the virtual test and the real test on the instrument machine. And you can see the cracks here. So another thing that we did, and we published it recently a few months ago, was to take the fragments here, the fragments there, and the in vivo ones, and we compared them to see if the fragmentation is predicted accurately. And indeed it is, because that's what these three show. Here for 0 and 15%, they're reasonably close. So this is a cumulative frequency and diameter. Any questions so far? Yes? Okay, so the finite element software is, this is what the damage model does. Do you remember this? Okay, here. So this basically is the damage model. When you reach D critical, then the stiffness of the element is degraded to 0. That's how it models it, basically. Yeah? Yeah? Yes. Yes. So this is the, oh, you mean not the cumulative frequency like I have here? So sorry, hang on, just let me find this bit here. Yes. I haven't got the, you mean the particle size distribution like looks like, I haven't got that, because you can use the same data to plot that instead of what I plotted here. Yeah, but we do have it for both the in vivo, in vitro, and in silico, and they quite agree as well. They're quite close as this. That I don't know actually. Yeah, maybe we should have a look at that and see what distribution they're following. Yeah, thank you. Yeah, more questions before we go to? I got time, Thibaut, to talk about digestion a little bit. Yeah, yeah. Okay. Okay, this is the last thing I'm going to talk to you about, because I didn't have time to talk about this in the first lecture on Saturday. We're also trying to model not just what happens in the mouth, but what happens later on in your stomach, which is really, really hard. I mean, oral process is hard. I don't know if this is harder or just as hard. I don't know. But it's very important because it affects your metabolism. You know, so basically how starch breaks down into glucose from hydrolysis and then the action of enzymes in your mouth, and there's other enzymes that break down proteins in your stomach. How the sugar is released will determine whether you get a sugar spike or not, and if it does, then you might get, you know, this epidemic that we have now with type 2 diabetes and so on. So it's very important for human health, and the food industry is interested in designing foods which are basically enable you to control the disintegration of and make, you know, nutrients bioavailable, such that even though some rappers say that you have those nutrients, it does not mean that you're actually going to benefit from them. It depends on how the food behaves inside your gastrointestinal tract, whether you will access them or not. So what happens to the food in the, here is the basically the stomach, here is the entry, and this is the exit to the small intestine. So what happens to the, we're concentrated in this area here, although more recently we're trying also to model this, because apparently this is where all the nutrients are taken in at the beginning of your small intestine. But I'm only going to show you this bit today, the stomach. What happens to the food in here? There's mechanical loads, there's peristalsis of these walls. We've read some other recent literature which also says it's not just peristalsis, which is waves basically of the stomach walls, but also a squeezing, uniform squeezing of the material. And the idea is, again, to keep breaking it down. It continues what started in your mouth, you know, breaking down the food. You have hydration. If you have solid foods, when they land in your stomach, there's gastric fluids. But those gastric fluids also have some chemicals which will disintegrate the food. So all of these things need to get looked at. We started off with just that. But more recently, we've started to see whether we can move to include the other two processes. So the idea here is we've done this on simple starch gels, which you wouldn't really have as a product. Nobody would just take a starch gel and eat it. It's used more as additives. But we also looked at products, okay, which are starch-based products. And the idea is you take your gel or your product, you do some tests where, like on the instrument, like I showed you earlier, you're not just wanting to measure the mechanical properties, you want to measure them as a function of this exposure to the chemicals in your stomach. How do the mechanical properties change? Such that you can create a material model. This looks very similar to what I showed you on Saturday. But here, instead of just having deformations here, these are deformations, you also have this parameter F, which is the, as I'll show you in a minute, is a parameter which tells you how much starch has hydrolyzed. So basically the chemistry basically in here. Once you have that, then you can do in silico model of the stomach, and then you're going to try and validate it. Of course, here is a lot more difficult to validate. Either in vivo especially is very difficult, although people do that, or do some in vitro digestion experiments. But that's the aim. This is the initial work that we did on some products which are commercial products. They're starch-based, so basically they're like biscuits. So we assume that they're continuum. This was their how much, they're basically how what the formulation of the biscuits was, and we finally ground them to particles, and we collected the small ones. And on those small particles, we added water and PBS, because we're trying to mimic saliva, basically. All right, so this is the bolus that will enter your stomach. And this is what it looks like, so mixing it with water. And we used ratios of moisture to solid, which were found from MRI from solid foods to be representative. And you get cylinders like this, and you can do compression. You can also do rheological tests, as I've shown here. Similar things I showed you on Saturday, compression and shear. And we got the curves, stress-strain curves. These are plotted in terms of equivalent stress and equivalent strain from the two types of tests. And instead of modeling the dots as they were, we simplified it with the red lines. Okay, so it's elastic, perfectly plastic, and the plasticity is dependent on rate. So which is a simple model, and then we can put that inside your final element software. This is the geometry of the stomach. So the food enters here and exits there. To begin with, we just said we're going to ignore that J shape, and we're just going to have a straight shape like this. And here, this is a small section, because this is then axisymmetric once you do that. So it's a lot easier than that. So you imagine you cut a small section, a wedge of this. This is your model down here. So this yellow is, you imagine there's a spherical bolus that lands in your stomach. This is the stomach wall, which will undergo those waves, and it will squish this out. And this gray here, this box, is a Eulerian domain, which basically means that you got your mesh here, which moves independent of your material, such that you can simulate very large deformations. Otherwise, your mesh will get distorted if you use pure Lagrangian, and you're not going to get any results from here. So the beginning, we just did it as a solid in an empty stomach, which of course is not very realistic. But recently, we included fluid around the solid, and the video I'm going to show you is the result of that. So this is the section. This is the stomach wall. The red is the solid, and the blue is the water. And from here, what we can get is curves like this. So how much food you get? Food is basically the solid. This is the liquid. And these are the total components and how they're emptying with time, which is, of course, very important, how quickly the food transits from your stomach. And this is, of course, very important, because if the material properties change, the structure properties change of the material, food scientists know that is very important, okay, in the take-up of the micronutrients. Yes? I'm not aware of that, because I think MRI is, you're going to have to lie down, and then the stand, yeah. But it's difficult, I think. You're lying down to digest. I think there are MRIs, which Adam knows more probably, that allow you to stand. Yeah. But what people do Yeah, and the other thing I know that people do is to have volunteers that come in and eat whatever it is they're going to eat, and they get intubated from here, and it goes all the way down to the stomach, and they collect samples from tubes. But of course that, in effect, is difficult because once you're pulling the food out of your stomach in those tiny little tubes, maybe it does break the material as well, so you've got another process going on there. So what we're planning to do is there's in vitro digestion models which are big contraptions, basically. They're called Tiny Tim. I don't know if anybody knows about them. That they try to simulate the various compartments of your gastrointestinal tract with vessels which are inside liquid, which then you change the pressure of the liquid, and those vessels get squished in and out at different parts of your stomach. So we're collaborating with someone like that. So we're going to try and model that, and then we see whether our models are working, are basically agreeing with those data. That's what the plan is. More questions? Okay, so we talked about this. Right, so how we're going to do this chemomechanical model. So here I've got some slides on the study that's going on at the moment on just pure starch gels. So we take starch, I think it's potato starch, with water. We stir it, heat it for 40 minutes until it gets 100% gelatinized. You make the gels, which are, I'm sure you can just about see them here. They're white, unfortunately, but you can pour the material into molds to make different cylinders. They're very solid. So here I have small cylinders, about 5 millimeters, medium and large, so 12.5 and 20 millimeter in diameter. And then we put them inside. So these are my cylinders, the large, medium, and small, if you can just about see them. We put them inside this liquid, which is alpha amylase, which breaks down the starch, which is produced in your mouth at 37 degrees, and then take the samples out at 30, 60, 90, 120 minutes and test them and compare them to the control, which is the ones that didn't go into this liquid, right? So no exposure. This is just a video of one of these tests to show compression. And on this axis, you have stress and strain. And you can see the unloading part as well. And we do these tests for cylinders which have been on the control, as well as those that have been exposed. So here, the legend, 0, 30, 60, 90, and 120 means how many minutes they've been in that liquid with the amylase. And here is the large samples, the medium-sized samples, and the small-sized samples. And you can see on all of these three, you start off from the 0, which is the ones that are the control, and there's the black lines. But then as you put this stuff inside the chemicals, all of these stresses are dropping, right, as you would expect. And you can see that the change here is not as big as here or there. Why do you think that is? Is that what we would expect? Yes? Correct. Yeah. So basically, if you assume this is diffusion, there's a much larger area here than here. So this basically the enzyme can go into the volume much, much faster than the medium and the larger. So this is what we were expecting, and we get reproducible results. So we were quite happy with this because we never did anything like this before. And then we're going to feed it to a model like this, very similar to what we talked about on Saturday. You got your dashpot and your two springs, these are hyperelastic strain energy functions, exactly the same as we discussed on Saturday. And then the difference is, as I showed before, is that we're going to make these functions also a function of F, where F is the hydrolysis fraction. It's 1 minus the starch concentration that you have now divided by the starch concentration you had at time 0, right? So if your starch is the same as it was before, so this will be 1, and then the hydrolysis fraction 0, it means nothing's happened to your gel. And so on. As it increases, it means you've increased your hydration. So the first thing that we did is to fit this model into our data. So this is the strength strain curves. So we calibrate, all of those are the parameters of the model, and F. Okay, so this is F, this is hydrolysis ratio, as I shown earlier, and you can see that F here increases as you increase the time of exposure in those liquids. So now we have F as a function of time, 1, 2, 3, 4, 5 points. Okay, so I can get the hydrolysis ratio as a function of time, and this is where we're at the moment. So this is a plot of F versus time. I've got my 0, 2, 3, 4, 5 points, the data, and then we filled this kinetic model, which is a very common model apparently in the literature, which shows you how the starch degrades with time. E here is the enzyme concentration, and the things in blue are parameters which you can now fit because you got those data. So basically what we're saying here is that this is the liquid in your stomach, and these are the enzymes, and this is your solid bolus, which has liquid as well as solid, and this it diffuse into your material and then start eating up your solid. And we're hoping, this is where we're at the moment, we're hoping now to be able to finish off these chemomechanical models such that we can put it into a finite element simulation and see what happens to the food as it gets interacts with the liquids. Yes? Yeah. I know. Well, to be honest with you, when you're eating, the saliva, the enzyme is actually getting quite well mixed in the bolus. So basically, when the bolus reaches your stomach, there's people that say that it's all mixed already. Yeah. It's very complicated. And we decided, you know, if you read this stuff and you think, oh, I won't be able to do anything, but you have to do something and see if you can validate it with the experiment, which is that in vitro stuff. And at least you make a start. And then, you know, slowly, slowly you try and get closer to the real thing. Yes, sorry, someone else had a question. Yeah. Mm-hmm. 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 Yeah, but it'd be very nice to talk to you, actually. We see if we can, because it's all new to us. So we're looking for people to help us with this. So please do get in touch if you've got better ideas of what we should be doing. Yes. Okay, so in your stomach, I think the pH changes and it deactivates. That's another problem with this. That people say, why are you doing the starch hydrolysis? Because the starch is in your mouth, but then when it goes in the stomach, the pH changes and it deactivates the starch. And it's more in the smallest intestine that you get. But, you know, as I said before, we have to do something. And then it's not going to be the real thing as a first step. Yeah. More questions? Okay, I think this is where the end of my slide. So as a conclusion, because I talked about various things, it will be the generic conclusions, is that you can use engineering to help design products to meet consumer demands, such as they still like them, the sweeten up, for example. I don't know, the sensories, like to get the right signature in sensory tests, but also look at people's health as well, how to design these products such that they're healthier. And research is progressing, not just in my group, but there's more and more papers on digestion and modeling digestion, and the more and more realistic these digestion models, which include these chemomechanical degradations. And as you have such digital tools that will help the food industry to make virtual tests, which will help, you know, how you develop new products, basically. Of course, you'll never be able to replace people actually tasting the material for sensory tests, but it will help in the design, to speed up the design. And then I think, yeah, that's just the acknowledgements for funding and the people who actually did this work. Thank you very much.